Hello, my name is Ahmed Bashar Medani. My student ID is 0379334. In this group assignment, I was mainly responsible for the data preprocessing, classification, anomaly detection, and the related visualizations. Our project uses the accidental drug-related deaths dataset from the state of Connecticut. The goal of this project is to apply data mining techniques to identify meaningful patterns from overdose records. In this project, the dataset was analyzed using classification, predictive analysis, clustering, and anomaly detection. Obviously, we have to first explore the data and taking a quick look at the data, you can obviously see that there are many missing values and so many inconsistent labels in the drug indicators. And we have some categorical variables that cannot be used directly in machine learning models. So I would have to apply data cleaning and some pre-processing. So the first one would be date conversion. We have to convert the date into a date-time format so we can actually use it. And then we have to convert every single drug indicator into a binary format. So here I just listed the top first frequent values are found in the other column, which is over here actually. We can see that some, well, it doesn't show anything here, but in some of the columns, there are some drugs that are just randomly stated there that aren't actually found in the columns. So I have to extract that from there. We can see that there are a significant amount that we can actually use, and it could probably provide us with some pattern. So now we're just standardizing all the text in there, so you can like make it all like uppercase or lowercase, just one specific format, so we can actually extract them, and then we will we'll definitely extract them, and then we'll create columns for them. These are the ones that are the most like significant from the ones that we extracted. Some of them were just repeated. Okay, so then we extract and merged some of the columns. We merged them with the original columns because some of them were just stated there for no reason. And we dropped any unnecessary drug indicators like the other opioid, any opioid, other and other clean. The other clean was used temporarily. We delete these because in the other opioid column, there was actually nothing to be extracted from it. It was just either a Y or an empty space. And we don't really want to know if there was another opioid. That doesn't really provide us with any pattern. We just unified all the morphine related columns because many of the columns they had like, yeah, it's right there, morphine, not heroin, morph, codeine. We just merge all of them together since they're basically the same drug. Then here I just clean the names of the extracted columns, and this would be basically the final preview of the clean or the preprocessing after cleaning or extracting the drugs from the other column. Now we will convert the main drug indicators to binary format, meaning I would convert them from a Y or an empty cell into a 1 or a 0, 1 being present, 0 being non-present. These are all the drug columns, excluding the ones that are already cleaned, are already extracted from the other column. We will ignore those because I already did convert those. So these are the ones that aren't converted yet. And this is just a preview. And then this is like a final check, which is like, so we can be 100% sure that we're not just converting anything and it'll be just like all ones or all zeros. Every single one of these drugs, they have a 0 and a 1, indicating there would be it'd be correctly converted into binary. Then we will have to handle all the missing values. First, we can tell here from the final drug columns, just as I showed right now, there are no nulls, so we're good. In the missing values, it's basically in age, sex, and race. I chose those because these are the most significant features for my applications. All the other ones, they just did not seem significant enough for me to fill in, or they just seemed impossible, like ethnicity, for example. That's just, you can't really fill in that in any machine learning model or application because we don't even have that much data to work with in that column to begin with. So the right decision would be either to drop it, and I wasn't even going to use it even if I had enough data to use it because my problem statements was different. And so we just check for the missing values in age, and then we replace it using the median. And then same thing with the sex and race, but I just fill in with unknown because you cannot really guess for sex and race. If you do guess, that's just going to bias the models. Next up, we will perform some data transformation. So I will be applying one hot encoding to sex and race, so we can convert them from categories into numbers that the models can understand. So I set unique sex values and unique race values. Sorry, I search for them, and then I will standardize the sex, and then replace anything that is like unknown with that is X with unknown. So the three sexes would be male, female, or unknown. And then same with the race. There's going to be these. These are the main. These would be the main ones. And then I will apply that one hot encoding, which will then preview the newly created dummy columns. And here it just shows the type. It was an integer at first, and then it converted again into integer 32, meaning we can actually use it. And this one in the middle, it just it shows for the actual like amount of cells we have or data we have with each of these races. Now I'm going to apply data reduction because I'm not going to be able to use all the columns based on my applications at least. We can just take a quick look at the shape again, and we can tell that there's obviously no duplicate rows, which is good. This is just for like percentages. This is just for me, so I can understand how much missing values I have of all of the columns. You can tell that by all of these, there are so many, but most of these are actually just free text, and free text. I didn't really use any application that would read or like extract free text, so I just ignored all of these. This checks for the high cardinality object columns, and we can tell there's so many of them, like here with the cause of death and all that stuff. And now I deleted all of these, all of the high cardinality and all the missing and the top ones that were missing, and I kept it into two data frames. A frame that had all the clean all the clean data, and then one that is reduced, which is the one I'm going to be using for the applications of, like in the modeling. And then for dataset preparation here, I actually just prepared the dataset for each of the implementations themselves. So this is just taking a look at the actual data frame, the data which I'm going to be using, and then this is just you can just see the common drugs. This is for to be applied later on. In the classification, I kept these features: the age, year, and then a couple of races, and obviously all the sexes. And then I just displayed a target distribution for fentanyl, because fentanyl is the target here in the classification. It is unbalanced, so that's why in the implementation I'll be applying stratification. In the prediction dataset, I just displayed the common drugs, the ones that are significant, and then I aggregated the total deaths per year and each common yearly drug count. For the clustering dataset, I would scale age and year, since they have a huge impact on the rest of the drugs, since they are all zeros and ones, and obviously for sex and race. In anomaly detection, I would gather the one hot encoded columns, the age and the year, and all the drugs. So this would be the final shape, and these are the number of features. I also specified I didn't specify. I found out the rare drugs in the anomaly dataset, which will help me really understand the results later on. For the association rules, I'm going to be ignoring that because I'm not going to be applying it this time. And obviously, saving and saving the clean data set to Excel so we can. Now I'm going to be explaining the actual implementation. The goal of classification was to predict whether an overdose case involved fentanyl. For this model, the input features were age, year, sex, and race, um, while fentanyl is used as a target variable. Since the target has two possible outcomes, this becomes a binary classification problem. For the task, I used a decision tree classifier right here. This method was chosen because it's simple, interpretable, and suitable for structured tabular data. It can handle both numerical and encoded categorical variables. And it also provides feature importance values, which helps explain the model's decisions. So I just imported everything I needed, and then all the metrics. I first begin with splitting the data. You can tell here the training shape and then the testing shape. And then I initialized the instance of the decision tree model, and then I fit it on the data, and then saved, and then predicted on the test, and then saved it in the y_prediction. For the evaluation, the model achieved an accuracy of 77.72%, precision of 82.37%, recall 85.03, an F1 score of 83.68. These results show that the model performed well, especially in identifying fentanyl-positive cases. The confusion matrix also shows that the model correctly classified 1,369 fentanyl-related cases and 494 non-fentanyl cases. However, there are still some false positives and false negatives, which means that the model was stronger in detecting fentanyl-related cases than the non-fentanyl cases. To validate the model further, I also applied cross-validation on fivefold. The average results were very close to the original train test results, which shows that the model was stable and not dependent on only one data split. For the feature importance, I just extracted the feature importance from the decision tree for every feature, so we can actually tell which features had the most impact on the decisions taken. We can tell that obviously year had the most, which shows that the fentanyl involvement is highly dependable on temporal involvement. Like anything, like it depends on the temporal features, temporal application. I'm going to be skipping prediction and clustering so that my teammate can explain it later on. For the anomaly detection task, in this part, the goal was to identify the unusual overdose cases that differ from the general pattern of the dataset. Since the unusual cases were not labeled in advance, this task is considered unsupervised. For this task, I used isolation forest. This method was selected because it is effective for finding rare cases in structured datasets without needing labeled anomaly examples. The anomaly dataset included the age, year, on-hot encoded sex and race, and clean drug indicator columns. The model was initialized with the n estimators at 200, contamination at 0.03, and random state 42. After training the model, it identified around 360 anomalous cases, which represents almost 3% of the data. This matches the contamination setting and shows them that the model flagged a small proportion of records as unusual. To validate the anomaly results, I examined the characteristics of the flag cases. A rare drug enrichment analysis showed that MDMA had the strongest enrichment, along with ketamine, which also showed slight enrichment. In contrast, difluorofentanyl and U47700 did not show any meaningful enrichment. This suggests that the anomaly model was able to detect certain cases associated with the uncommon drug patterns, especially the MDMA-related cases. I also compared anomaly cases with normal cases. The anomaly cases had a slightly higher mean age, occurred in slightly later years on average, and had a lower fentanyl rate than normal cases. This indicates that the model was not simply detecting fentanyl-heavy cases, but was instead identifying broader unusual case profiles. Now, to visualize I actually used a local LLM using it's running locally on my device, and then it's just using this API to send it the prompt and then receive it here and then actually display the generated code. So here I ask it to return me the code and then to execute the code in the chat. So here you can see for the first visualization, I visualized a heat map of the confusion matrix that we saw earlier. This is the code for it, and then this is the actual visualization. This is the same thing. It's just that it's more visually pleasing, and anyone, like if I was about to show it to someone else that doesn't understand anything about about classification or about model machine learning in general, they could probably understand this with a few explanations. As we saw earlier, the 494 and the 1369 correctly predicted class labels. The next one would be a simplified decision tree. I asked the LLM to generate me the decision tree itself. This is how the tree decides on the next important feature. We can see here that it first decides on year, and then it decides next on age. On the right side, you can see that it mostly detects for the female, while the left side it's mostly on age and year. And on the left side, it's actually 2015, 14, and then 13. On the right side, it's in the later years, like 2018 and all that other stuff. For anomaly detection, I only visualized one visual, which is the rare drug enrichment analysis, as I did before. This just shows how significant the enrichment is for MDMA compared to its normal rate, and the others, like for ketamine and its normal rate, and for difluoro and U4770, it's actually below 0, meaning that there was no enrichment in either of those. That concludes my part of the presentation, which covers data pre-processing, classification, anomaly detection, and the related visualizations. I'll now pass my presentation to my teammate, who will explain the predictive and clustering parts of this project. Thank you.
Hi, my name is Liu Kenneth, and my student ID is 0372933. In this project, I was mainly responsible for the prediction analysis, clustering analysis, and their related visualizations. So in this presentation, I will explain the predictive model, the clustering analysis, the visualizations used to support this analysis, and finally, the overall conclusion of the project. Okay. First, we'll start with a predictive analysis. So for the predictive task, we use a linear regression model to analyze the yearly trend of drug-related deaths. So the main goal of this model was to observe how overdose deaths change over time and to estimate future death counts based on the historical data. So to prepare the data set, first grouped the overdose record by year and calculated the total number of deaths for each year. So this created a summarized data set containing yearly totals from 2012 to 2023. So giving us 12 observations in total. So in the regression model, year was used as the input variable, while total death was used for the target variable. This allows the model to learn the relationship between time and the number of overdose deaths. So next, we perform a time-based dataset split. Instead of randomly dividing the data, we use the earlier years for training and the later years for testing. Specifically, 70% of the data from 2012 to 2019 was used for training, while the remaining 30% from 2020 to 2023 was used for testing. This approach reflects a realistic prediction scenario where past data is used to estimate future outcomes. So after preparing the data, we train the linear regression model using the training data set. The model learns a regression equation that estimates the relationship between the year and the number of deaths. The regression model produced a coefficient of approximately 112, which means the model estimates that the number of overdose deaths increased by around 121 deaths per year on average, according to the trend learned from the training data. After training the model, predictions were generated for the testing years from 2020 to 2023. These predictions were then compared with the actual death counts to evaluate the performance of the model. Coming to the evaluation part of the predictive model, we use several regression evaluation metrics, including mean absolute error, root mean square error, and the R-square score. So the results show that the model achieved a mean absolute error of about 150, which means that on average, the predicted death count differs from the actual value by about 150 deaths per year. And the root mean square error was around 199, indicating that some prediction errors are slightly larger. However, the R-square value was negative, which means that the regression model does not explain the variation in the dataset very well. This is mainly due to the small size of the dataset and the fact that the number of deaths does not follow a perfectly linear pattern across the years. Even though the prediction accuracy is limited, the regression model still helps illustrate the overall upward trend of drug-related deaths over time, which provide useful insight into long-term pattern in the dataset. Next, I will explain the clustering analysis. So for clustering, we apply the k-means clustering algorithm, which is an unsupervised learning technique used to group similar data points together without predefined labels. So in this task, several variables were used to describe each overdose case, including age and multiple drug involvement, indicators such as heroin, cocaine, fentanyl, methadone, and other substances. So these features capture both demographic characteristic and drug-related patterns in overdose case. To determine the most suitable number of the cluster, we use the elbow method. So the elbow method, the k-means algorithm was tested using different numbers of cluster ranging from 2 to 9. And for each value of k, the inertia value was calculated to measure how compact the cluster was. From the elbow plot, we observe that the reduction of the inertia begins to slow down at k equals to 3. So, which indicates that 3 cluster provide a good balance between model simplicity and clustering quality. So, and after selecting 3 cluster, we train the k-means model and assign a cluster label each record of the data. The results show that the data set was divided into 3 clusters with relatively balanced size, so containing approximately 3,965, 3,879, and 4,137 cases respectively. To evaluate the clustering quality, we calculate the Seal-Holted score, which measure how well each data points fit within the cluster compared to other cluster. So the clustering model produced a Seal-Holted score of around 0.18, which indicates that the clusters have some separation but are not extremely distinct. So this is common in real-world dataset where many cases share similarity in characteristic. Next, I'll briefly explain the visualization used in the predictive model. So the visualization show the actual number of deaths and the predictive regression trend over the year. So this helps illustrate the general pattern of overdose death and allow us to compare predicted values with real observation. And for the clustering analysis, visualizations help display how overdose cases and distribute across different clusters. So these variations make it easier to observe the patterns of age groups and drug involvement characteristic among different cluster groups. And finally, I'll conclude the findings of this project. So in this project, we apply several data mining techniques to analyze patterns in accidental drug-related death, including classification, prediction, clustering, and anomaly detection. So overall, this project demonstrates how data mining techniques can reveal predictive relationships, hidden group structures, and unusual patterns within drug overdose data. They are not immediately visible in raw dataset. Among the 4 tasks, classification achieved the strongest performance, while the predictive models was more limited due to the simplicity of linear regression. And in the future, prediction accuracy could be improved using more advanced time series or non-linear forecasting model. Clustering or anomaly detection could benefit from incorporating additional features and validation methods. So to end, despite this limitation, the project successfully achieved its objective and applying multiple data mining techniques to uncover meaningful patterns and insights in accidental drug-related deaths. And that's all for the project.